Hi folks, this video we're going to talk a little bit about variable stars. And variable stars are stars that change their brightness over time. We'll explain eventually how exactly this happens, but there are three major types of variable stars: long period variables, Cepheid variables, and RR Lyra variables. This is a wonderful illustration right here. If that is the sun and the circle around it represents the Earth's orbit, this one individual star, you can see that it starts out in May of 2005, relatively small. By October the same year, it's maybe doubled the diameter of the Earth's orbit. By May of 2006, it's actually, I think, a little bit smaller or similar to what it was the previous May. And then by March, you can tell that it's growing a little bit. So what's going on? You have stars that have a lot of brightness. They slowly get dim, and then they get bright again, and they slowly get dim. These variable stars are incredibly useful for determining the distance to stars. Now, first off, long period variables. Long period variables are stars that take their sweet time in changing luminosity. It can take months or it can take years. Common example is the star Lyra in the constellation Cetus the Whale. And this is an illustration of a Lyra type long period variable. And it will go from being relatively small to being maybe double size and eventually go back again. So it will change over time. The most famous type of variable star are called Cepheid variables. So I'm going to play Mr. Rogers, and I'm going to ask you to repeat after me. Cepheid. Cepheid. Yeah, it's a funny word. It's got syllables in weird places. Why does it have such an odd name? Cepheid variables are common because there is the delta Cephi, which is the delta star in the constellation Cepheus. Here's a picture of the constellation Cepheus, and delta is this little star right there. And that star actually changes its luminosity or brightness over time. What happens with these Cepheus variables is they get very, very bright, and then slowly over time they get a little dimmer. Very bright, slowly over time they get a little dimmer. And that's these Cepheid variables. Now, this will happen with a Cepheid variable over days or weeks, which is pretty fast. Anything that happens that fast is amazing in astronomy, because we're talking about things that are very big and very old. Why do we care? We care so much because there is a direct relationship between how long it takes to change its brightness, how much time it actually takes to change its brightness, and how bright the star really is. So if you have a star that is of a certain brightness, it will take a set amount of time for it to change that brightness from brightest to dimmest to brightest to dimmest. If you have a star that, I'm going to pick another color here, let me pick purple. If I have another star that I'm just going to hand graph, and maybe it gets brighter and dimmer slower, and then brighter and dimmer slower. The purple star that I'm drawing that goes through this oscillation of brightness to dim in a shorter period of time, there is a direct relationship between the time it takes and the brightness of the star. Well, why is that a big deal? If we can determine the brightness of a star, and we know that this star compared to planet Earth is a long, long, long way away, and we can figure out its absolute magnitude, its absolute brightness, then we can back calculate its distance. Because remember, the only simple way to calculate distance is by this concept of parallax. If here's the sun, and as the Earth orbits from one side of the Earth's orbit to the other, if we see a star change its position against the background as the Earth changes, using that parallax method, we can determine how far away a star is. But so many stars are at such a huge distance, that technique just won't work. So we've got to have something better. And that's what the Cepheid variables do for us. If we can just time it, we can determine the absolute brightness, and with brightness, we can then determine distance, how far it is from that star to the Earth. So it's a little bit fussy. It takes a couple steps you've got to go through in order to find that distance. But it's by doing that that we have been able to map the universe. How far away are stars and black holes and nebula and galaxies? How did we determine this relationship between brightness and distance in the first place? Well, we did that in the first place using stars whose distances we knew via the parallax method. So it's a lot of different data, a lot of experiments that were done through time, in order to give us that information. So what causes a star to vary its brightness or its magnitude? First off, the stars that are variable are all very, very old, and they're dying. As a star is in the middle of its life, it has a tug of war. Gravity is constantly trying to pull that star inward, and the heat and the pressure of the hot gas is trying to push that star outward. If you have a stable star like our sun, those things stay nice and stable, and they are equal in inward gravity and outward pressure, and it gives you a nice stable star. But when a star starts to be very old and dying, what happens is it stops being able to produce enough heat to keep the big balloon blown up. And what occurs is the star blows up, and then very, very slowly it kind of goes poof, 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 and it releases gases out into the solar system around it. So a star gets hot, and then slowly puff, 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 it releases gases outward, and it shrinks again. And it goes up, and then puff, 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 down it goes. What happens to all the gas that it's puffing out and ejecting out to become a new nebula? Well, that is leaving the star, and the star can only do this for so long before the star just dissipates itself away. So that's why Cepheid variables are always in, or all variable stars are in, old and dying stars. The woman who actually discovered Cepheid variables is Henrietta Leavitt. Henrietta Leavitt, again, is one of the Harvard computers. She found this relationship between the period of time it takes a star to get big and then slowly that bubble of gas to get smaller. She found a relationship between that time and the luminosity or the brightness of that star. So she is one of those names you need to know in astronomy, is Henrietta Leavitt, who discovered Cepheid variables. These are useful, as I mentioned before, to finding the distance to distant stars and distant galaxies that are just too far for that triangulation method. With this new tool, we are able to find the distances to the most distant objects in the universe, because if we find a galaxy out there, we don't have to find the distance to every star, but we find the distance to maybe one star. You find the distance to that one star, you then know the distance to the entire galaxy. Third kind of variable star is called the RR Lyra variable, named for the star RR in the constellation Lyra. And it is, the constellation, as you remember, is a huge area of the sky, and they are named in order from brightest to least brightest. So RR is pretty dim most of the time, but RR variable stars vary quickly, very, 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 very fast, in hours, not days. So RR Lyras are hours, Cepheid variables are going to be days and weeks, and those long period variables are going to take months or years. So there's not necessarily clear definitions between these, but it's very fast, pretty pokey. Where do we find our Lyra variables? Commonly found in clusters of stars, groups of stars that are all born at the same time, and hence they're like a litter of puppies or a litter of kittens. They're all born pretty much at the same time, so they're all pretty much the same age. All right, that's going to conclude our discussion of variable stars, and next we're going to talk about star clusters.